Hello everyone. This week we're going to look at the last chapter of our Physics 11 year, which is electric circuit, something that you have learned in previous science class for a little bit already, but we are going to go into much more detail. So let's start by looking at some fundamentals. We will about these atoms. So this is an atom which it has neutron, protons, and electrons, right? So fundamental particles like these, proton, neutrons, and electron, makes up everything in our universe. So proton, neutron, and electrons. Now, they make up everything in our universe. These particles have different properties. So for example, they do have different size, the proton and neutron being slightly bigger, electron being very small, and different mass. And one last thing that they also have is they have different charge also. Now you might remember learning about positive and negative charge or neutral charge in previous year. But what is charge? What is actually charge? Now, charge is actually a fundamental property of matter, just like mass, and is measured in coulomb. So the unit for mass, for example, is kilogram. The unit for charge is coulomb. So we measure charge by coulomb. Now, coulomb is named after a French physicist, Charles Coulomb, and you have his picture right here. He's also the same person that invented the friction equation, the mu Fn, friction equal to mu Fn. So thank him for that one too. Now, coulomb, usually when you write down something's unit, you don't write the whole word, right? So a lot of time we just use the shortcut C, so coulomb C, so 1 coulomb, 2 coulomb. Now you might say, okay, so is an electron 1 coulomb of charge? Not really. A coulomb is actually a unit that's quite big. Just like, for example, is the mass of a proton 1 kilogram? No, you need like trillions and trillions of proton to make 1 kilogram, right? So coulomb, I'll talk about that in a little bit, is the unit of charge, and I'll show you how big is the charge of 1 electron and 1 proton. Okay, so I have this little conversation, imaginary conversation between me and my son. So Atlas, my son, right? So, but daddy, what is a charge? Well, no one really know. I mean, seriously, no one really know what charge is. Just like no one really know what mass is. We know that anything has charge and anything has mass. The only thing that we are able to confirm for now, so far, for the past thousands of years, is that there are 2 types of charge. Some are positive. So for example, a proton has a positive type of charge, and something like an electron has a negative type of charge. Okay, so we know that there are 2 types of charge. Okay, so positive and negative type. And we also know that how they interact with each other is by something called electric force. So opposite charge, so if you have 2 charges that are of different types, so for example, 1 positive and 1 negative one, then what happened is there's actually a force attracting them to each other, and it's called electric force, which is something you learn in physics 12. So opposite charge, okay, so opposite charge attract each other. Okay. And light charge being, for example, when you have 2 charges that are the same. So for example, if you have an electron and an electron, so this is light charge, then they actually repel each other. So there is a electric force on each of the object pushing them away. Now you can also do that with 2 protons. So light charge repel. Okay, opposite charge attract, light charge repel. That's all we know so far. There are 2 types of charge. We don't know why it exists, but we know that it's there. Negative repel, positive repel, and opposite charge, negative positive attracts. Okay, so now let's list their properties. So proton, usually the symbol is P. Neutron, usually N. Electron, usually this little E. Now sometimes just to show their charge, we also put like a little superscript of a positive and negative. So neutron is neutral, so no charge. Proton is positive, so positive charge on the top, and electron. Now the mass, so they have different mass too. So for example, a proton has a mass of 1.67 times 10 to the negative 27 kilograms. So it's really, really small. It's 0.20 something 0 later 167. It's a very, very small number. Now, neutron turns out to be approximately the same mass of proton. They're so close that we can almost say that they are the same. Okay, so neutron, proton, approximately the same mass. Now, you won't be tested on this. If I ever actually ask you to calculate something with mass, I'll give you the mass, so don't worry about that, just for reference right now. Now, electron, though, however, is very special. Electron has a mass that is much smaller, actually almost 1,000 times smaller. Electron has a mass of 9.11 times 10 to the negative 31, and it's measured in kilogram, of course, all the mass. So this is like 1,000 times smaller than proton. So proton and neutrons are very heavy. They're in the nucleus. Electrons are very, very light. Now, however, though, if you only look at the charge, now let's go to the charge. So you might say, okay, so Mr. Chang, is a proton 1 coulomb and electron negative 1 coulomb? That would be easy, right? That would be very nice. But unfortunately, that is not how it works. So 1 coulomb is like 1 kilogram. Is proton 1 kilogram? No, you need billions and billions of proton to make 1 kilogram. So the charge of 1 proton is 1.6 times 10 to the negative 19 coulomb. Okay, again, it's a very, very small amount. Okay, so it will take you billions and billions of proton to make 1 coulombs of proton. So every proton has a little bit of charge, little bit of positive charge. I should restate that a positive 1.6 times 10 to the negative 19 coulomb. Electron has exactly the same amount of charge, except is negative. So this charge value is called the elementary charge because it is the fundamental charge of like everything that we have. So it's either you either have protons or electron or both. Now, neutron has no charge, so we don't have to worry about neutron. Okay, but for our chapter, our focus will be on the electron. Okay, so electron has a negative charge, and the amount of charge is about 1.6 times 10 to the negative 19 coulomb per 1 electron. Now, can you have 1 coulombs of electron? Sure. It's like you ask me, Mr. Chang, can I have 1 kilogram of sugar? Sure, I'll have to give you a lot of grains of sugar, but I can give you 1 kilogram of it. But each grain of sugar is not 1 kilogram, right? So each electron itself is not 1 coulomb. Each electron is a very tiny amount of coulomb of charge negatively. Okay, so now you should have learned that already. So I'm just trying to do review in here now. But if you haven't, that's okay. That's okay, right? Okay, so the next part. Have you ever wondered how? Okay, so how does that fit into anything? Have you ever wondered how energy is delivered to any electronic devices? For example, you have your TV, you have your cell phone, and you know that you have to plug them in order to charge them or turn them on, right? You have your PlayStation 4, your Xbox, same thing. Computer, same thing. Energy comes from something. It comes from the AC outlet, the power outlet in your house, or it comes from a battery, like a portable storage device like a battery. But nothing is going to happen if you just take a battery and you put it on the table, and you take for example, your remote control, and you just leave it like on the side. Nothing's going to happen if the battery is here and your remote control is over there, right? The remote control is not going to work if your battery is outside of it, right? You have to somehow make the energy from the battery goes into the remote control, right? So for energy to flow, you need a few basic things, okay? So first, you must provide a pathway, okay? You must provide a kind of connection between them. So for example, I have a light bulb here, I have a battery here. So how do I power the light bulb? Well, I can't just magically view them into connection. I have to actually give them a wire. So I will have a wire, and I will collect one end of the wire to the positive terminal of the battery, and I have collect the other end of the wire from the other part of the light bulb to the negative terminal of the battery. So now there's a pathway, okay? And then, okay, so first we need a pathway. Second, we will need a power source. We will need an energy source. Okay, now the energy source is the item that's providing the energy. So in this case, the energy source is the battery itself. Okay, or the AC outlet. It could be the AC outlet if you're plugging it in instead of using a battery. The first thing for a circuit to actually function is actually something that can use the energy. You cannot have a circuit that's just a battery collecting to itself. Now that is a very dangerous thing, and that will cause a fire. For example, if you have a battery collected to itself with nothing in between, well, who is actually using the energy? Think about it. It's like you are feeding the wire a lot of energy, and the wire is like, okay, so I'll carry this energy to somewhere, but no one is there. When no one is there, what happened? Well, then the energy gets sent back to the battery, and what? And it burns up the battery. So this is actually one of the way that accident could happen in your household when wiring are not done correctly, right? Now, so we have to avoid that, right? So we need something that can actually use the energy, that can actually consume the energy. Now we call that in a circuit a load. Okay, something that is used, something that's there to use up the energy is a load. For example, the light bulb is a load. Your PS4 is a load. A resistor, hopefully you still remember what resistors are from science class, is a load. Or your speaker or anything that uses the energy that you're delivering with the battery collected to it is a load. Okay, so on top of that, now it seems to be pretty good as a picture, right? We need something else? Yes, we need one more thing. We need one more very important thing. The energy stored in the battery. Who is going to take those energy and go to the light bulb? Someone has to take the energy from here and actually walk this path and go to the light bulb and deliver it, right? And that is the job for an energy carrier. So we need someone. So we need an energy carrier. Now, we have been in this quarantine for a while now, so a lot of people have ordered takeout and delivery. Someone has to deliver the food to you, right? So someone has to deliver the energy from the battery to the light bulb. So Uber Eats, do we call Uber Eats? No. We call electrons. Electron are the one who actually does this for us. So we inside the battery, we have electron going in empty-handed and electron coming out with energy. And it's deliver the energy. So what happened is this little electron is going to, now if I can select the electron, just one moment. So this little electron is going to take the energy and then travel through here. And then it's going to go to the light bulb. And it's going to dump the energy in the light bulb. So after it exits the light bulb, it will actually have, well, no more energy. And then it will then go back to the battery and it's going to pick up more energy and do that again. So it's actually the electron that are doing this for us. Okay, so it's the electron that's doing this for us. So electron is an energy carrier. So now, do you understand what a circuit is supposed to have? You have to have four things, technically. You have to have a power source. Okay, let me highlight things that I'm talking about. You must have an energy source that's providing the energy. In this case, energy source battery. You must have a pathway. A pathway are the wires. Okay, they're usually just the wires. So that there's a role for you to deliver the energy to the object. The object that's using the energy is called a load. Okay, it could be anything. The light bulb is just the easiest example we can think of. Anything that uses electricity, your microwave, your PlayStation 4, your iPhone, anything that uses energy is a load. Now you might say, Mr. Chang, but I don't have a wire collecting a battery to my cell phone. There is. It's inside your cell phone. I'm not suggesting that you take apart your cell phone because you might not be able, actually, it's very likely that you won't be able to put it back. So please don't do that. If we ever had a chance, next year to meet face to face, Mr. Chan will show you maybe a phone that's open so that you can actually see there are wires that connects the battery to every single part of your phone inside. It's inside, right? They don't want to see the wire outside. That's ugly, right? So you must have a load. And the fourth thing, which is very important, is there must be some kind of carriers for the energy, in this case, electrons. Okay, moving on. Now, then let's talk in detail. What is voltage, what is current, and what is resistance? Those are the things that you learn in previous science class, but do you really, really understand what they are? And how does that relate to what we are doing right now? Voltage. Okay, so voltage, also known as potential difference, is the change in the potential energy per unit charge. Now that is the standard definition of what voltage is. But I would like to use a slightly more down-to-earth, easier to understand definition of it. basically, the voltage of a battery is the amount of energy carried by 1 coulombs of electron. Okay, so what does that mean? Now, remember I said those electrons are technically just carriers for the energy, right? So imagine that this dude, or lady, this girl right there is an electron, and she's carrying 1, 2, 3, 4 pieces, right? Now, let's say every piece is 1 volt of energy. Every piece is 1 volt of energy. So she is carrying 4 volts. Okay, so that's an analogy we can use. So the definition of voltage is what? Voltage is the amount of energy carried by 1 coulombs of electron. Now, in this picture, V is voltage. So in this equation, V is voltage, which is measured in volts. Yeah, I know, it's annoying. The symbol for voltage and the symbol for and the unit for voltage is exactly the same. So voltage is measured in volts. Okay, volts. Okay, and then now energy, of course, energy that's carried by the electron. So it's actually electric potential energy is measured in joules, right? Energy is measured in joules, just like the last chapter. That's the reason why we're doing this chapter after the last one like that. And the last object, the last item in here is Q. Now Q is the symbol in the equation for charge. Okay, charge, you know the coulomb thing? Yeah, the charge. Now we are counting charge by coulomb. Okay, by coulomb. So C is actually just coulomb. So we're counting charge by coulomb. But remember, this, now I don't want you to think about this as 1 electron carrying 4 joules of energy. So let's look at that definition upstairs. So for example, now you know that sometimes, so let's go back to the last, you know this type of battery, right? We call them 9-volt battery because it says 9 volt on them. And then we have the smaller, the AA battery, which is a 1.5 volt battery. So what's the difference between a 1.5 volt battery and a 9-volt battery? Okay, so what's the difference between them? What is voltage, right? So for example, now, so the way I think about this is if you have a 1.5 volt battery, that means the electron carries 1.5 every coulombs of electron. Now you have to kind of run with me in here. So we're not talking about 1 electron. We're talking about 1 coulombs of electrons. So many of them. And they have a little backpack because they are the Uber Eat people for the electronics. So they have a little backpack. And inside the backpack, they carries energy. So a 1.5 volt battery has electron coming out carrying 1.5 joules of energy per coulomb. And it's going to take that energy, that 1.5 joules of potential energy, and it's going to deliver it to the light bulb. Okay, so it comes out from the battery, it goes through the wire, it delivers the energy to the light bulb. Now, after it passes through the light bulb, it will have no more energy. And then what happened? Well, then it will take its turn and return back to the shop. Okay, return back to the battery. And once it goes to the battery, now it goes through the battery and it picks up what? It picks up 1.5 volts of energy again, 1.5 joules of energy again. So that's how it works. Now, so what happens if you put a 9-volt battery in there? Now, a 9-volt battery is only different in one simple thing, which is when you have an electron coming out and you look at the electron's backpack, instead of having 1.5 joules of energy, it will have 9 joules of energy coming out. So for example, if the electron take that and deliver that energy to a light bulb, the light bulb will be much brighter because it's consuming more energy. The more energy you let your machine consume, the brighter, the louder it will actually work, right? Okay, so what is voltage in a sense? So voltage is the amount of energy carried by 1 coulombs of electrons. Okay, so let's write that down in here. So for example, so when you have a 9 volt, okay, so what does 9 volt battery mean? 9 volt battery, So 9-volt battery means that, an electron, so every coulombs of electron. Now remember, we are counting by coulomb. So every coulombs of electrons carries, so this little E symbol is electron, okay? Carries 9 joules of energy, or picks up 9 joules of energy when it goes through the battery. Okay, when we talk about voltage or the energy, we always talk about the difference in energy. So for example, when the electron goes through the battery, it picks up 9 volts. It picks up 9 joules of energy. We call that 9 volt. Every coulombs of electron carry 9 volts of energy. So you can carry more. Okay, so you can carry more. So for example, look at this electron, this electron right here. Count the number of pieces. 1, 2, 3, 4, 5. So this is a 5 volt carrying electron. So it could be, with different combinations of battery, you can actually make the number whatever you want. Okay, so voltage, once more, is the amount of energy. So that's why we have E in here, is the amount of energy carried by 1 coulombs of electron. Okay, so E over Q, amount of energy carried by 1 coulombs of electron. Okay, now let's move on to the definition, the next definition, which is what is the current. Okay, so voltage, right? Now, when I was younger, I think when I was in grade 11, I actually make up an analogy called the pizza delivery model. We'll talk about that in detail just a bit later on, right here. Okay, right now I'm using some of those terminology. So I think of electron as the people who deliver the food, like the Uber Eats people who are the drivers, right? And I look at the energy or the voltage as the pizza that they're carrying. Okay, so let's say I order pizza. Well, I order 4 pizza, then the person delivers 4 pizza to me. That's 4 volts. So the amount of pizza that the electrons are carrying, or the amount of energy that the electrons are carrying, is the voltage for me. Okay. Now, what about the electron itself? Current. Okay. So the next part, current. Current is the rate of flow of electrons through the cross-section area of a conductor. Now, remember, the conductor is just something that collects the circuit and complete it, which is usually just a wire. So that means, in a more simple term, current is the amount of electron going through the wire every second. Going through the wires every second. So the definition of current is this equation right here. Current. Now the symbol for current is I. I apologize for that. So I know it's not the first letter, but because C is already used for many, many things. So current, I, is equal to the amount of electron charge, which is measured in coulombs. So charge per unit time. So divided by time. So T stands for time, which is measured in seconds as usual. Right? So T is time, which is measured in seconds. And then we have Q, which is the same thing as before, right? So Q is the charge. So these are the same thing as before. So charge measured in coulomb, and I is the current, and current is measured in M. So current, now, on the other hand, so current, the unit for current is ampere or M. And so current, the unit, okay, so look at units here, unit ampere. It's named after a scientist. Or a lot of time people just say amps, 5 amps, 2 amps. Of course, the symbol, if you want to just talk about the shortcut, is just A. Okay, so the shortcut version of everything is for the current is just A. All right. Now, what does that mean? Okay, so imagine that you have a wire. Okay, like that. Now, I'm actually drawing this wire so that it's very enlarged, so that you can actually, let's say you have a wire which is really small, but let's say you can actually cut the wire and use a microscope to see the microscopic level of what happens to the wire. And now you see 3 groups of electron. Remember, each of these delivery guy is actually 1 coulombs of electron, not 1 electron though. Don't make that mistake of thinking 1 electron is 1 coulombs of electron. It's like 1 tiny little grain of sugar is not 1 kilogram of sugar. Okay, I must stress that. Okay, so you have these electrons all carrying pizza for you. So how many electrons are moving in the circuits right now? Well, 3, right? I don't care how much pizza they're carrying. 3. So we said the current, okay, so the current is 3 amp at this part of the circuit. That means 3 coulombs of electron passes by some point every second. So we have to actually pick a point and ask what is the current through this point. So let's say we pick like a point in here and we say, okay, so if you wait there for a few seconds, for 1 second, how many coulombs of electron go through you? 3 coulombs of electron going through that in 1 second. That is 3 amp. So that's what 3 amp means. Okay, so 3 amp. Okay, so for example in here, so example, and let's write that down, definition. So for example, 3 amps means 3 coulombs, 3 coulombs of electrons are passing by a point in the circuit every second. Okay, so when they said the current at some point is 3 amp, that means 3 coulombs of electrons are passing by. 3 coulombs of electrons are passing by a point in the circuit every second. Now, of course, you can, just like, my pizza delivery models, right? Like most shops hire more than 1 person to do the delivery jobs. So maybe one shop hires 10 people, the other shop hires only 3 people. So that's the difference. So the current, in my analogy, are the electrons. They are the people who deliver the food for you, not how much energy or pizza they're carrying. So voltage is the amount of pizza that they're carrying, or the amount of energy that they're carrying. Current is how many of them are moving past a point every second. So this current, for example, 1, 2, 3, 4. So let's say these are all moving that way, and they within 1 second they all pass through that line. Then we will say the current in this location is 5 amp. Okay, so let me show you a little picture. I think I have it over here. Just give me 1 second. I think this is the picture I want to show you. So right here. So we have a battery. Okay, so we have a battery, like right there. There's a battery. And then we have a load, which is right here. And we also have a pathway, as you can see, which is completed. And we also have people who are delivering the energy. Can you see that? People who are delivering the energy are these little trucks. These little trucks are delivering the energy. They are the electron. They are the pizza delivery guy. So for example, you pick up 6 volts of energy. So they carry, can you see that? On their back, they carry 6 little, if you look at these ones right here, they carry every single one of those electron group. Remember, let's think about them as 1 coulombs of electron. Every single car, every 1 coulombs electron is carrying 6 joules of energy and delivering that 6 joules of energy into the light bulb. And after they go out, look at them. All the energies are gone. The voltage are gone. So they have to go back to the battery, pick up more energy, and do the delivery again. So what is the voltage on these electrons? Well, 6 volts, right? Simple. As they go through it, the voltage is going to be difference is going to be 6 volts because it drops 6 volts. Actually, in the battery, the voltage difference is plus 6 volts because you don't have anything, and then you go in and now you have something. But what about current? How do you measure current? You have to put a stop right there like that, and then count how many people go through you, how many groups of electrons go through you every second. I don't actually have a way of counting that right now. I think it's about 2 cars going through that line every second, or 3 cars going through that line every second. So that will be 2 or 3 amp. Okay, like 2 amp or 3 amp. So current is measured by looking at how many electron passes, how many coulombs of electron passes you every second. Okay, now let's go back to the note and finishing up down here. Okay, so now we have our resistance. So we have our current, we have our voltage, and just end this with resistance. Okay, so resistance. Now, resistance, the last item in here, resistance is a property of matter. Now, this specific property, and it's measured in ohms, OHM, ohm, and this omega symbol. So usually when you write it, you write this omega symbol. So some material, now, so it depends on what kind of materials you have. Some material have low resistance, and they are considered to be a good electric conductors. So for example, that means they conduct electricity really well. Now, that means those are the material that are perfect for making wires. For example, metals, right? Most metals are good conductors. Most of them. Irons are good conductors. That means electron can actually go through it quite easily, delivering energy for what we use. However, so they allow electron to flow freely. However, there are other materials that are not so good as a conductor. For example, wood, plastic, or even air are not actually good at that. They have really high resistance to the electron flow. So they are bad conductors. Now, bad conductors, so electrons have harder time going through them. But harder time does not mean impossible though. Okay, it's not impossible. Just like, for example, think about it. You can have a good road with not a lot of traffic, right? So resistance sometimes is actually best to be thought about as traffic. So low traffic, then you are good. Then this is a really efficient road, right? For example, metal has low traffic. However, wood, plastic, and air have a really, really bad traffic. But really, really bad traffic doesn't mean that the electron actually cannot go through it, period. It means that it has more difficult time going through it, and you have to really push it to go through it, right? So even though people say, hey, wood cannot conduct electricity, that's only true when the amount of energy is normal. If you have a lot of energy, it will go through anything. Look at lightning, right? Let's think about it. You have those electrical outlets in your home. There's actually energy inside, electron waiting to come out. But because air is a really bad conductor, those electrons doesn't come out and attack you and electrocute you, right? Well, unless you put your finger in it, which you should never do. Okay, you should never do that. Don't put your finger inside the the energy outlet. But those electrons are actually there waiting. They just can't go through the air because it's very, very, very high resistance for air. Air has very, very high resistance. But sometimes if the electron has enough energy, can actually go through the air. If you don't trust me, that's what lightning is. Lightning is when electron in the cloud has way too much energy that they can actually jump through air. They don't care anymore. Because they have so much energy. I don't care the traffic is bad. I'm just going to bully myself into the destination. They will actually jump through air when the voltage is high enough. Okay, so be careful. Now, I'm going to mispronounce this person's name. I will apologize. He's a German scientist. So, I thought his name was George, but it was German. So, it's actually Georg Ohms. Georg Ohms. Okay, so he's a German scientist who actually put a lot of time to study the relationship between voltage, current, and resistance. Now he realized that for material, you can have a power source connected to it. How much current actually goes through it depends on if the conductor is a good conductor or a bad conductor. Okay, it depends on the resistance of the object. Now he discovered that there is a ratio that you can write down. The ratio between the voltage and the current is called resistance. Okay, now this equation is more commonly known in this format, which is V equal IR. This is the famous, very, very important equation. I would say if you pick one equation that's the most important in this chapter, it will be this one, Ohm's law. Okay, this is called Ohm's law. Voltage measured in volts, current measured in amps, resistance measured in ohms. Okay, so this is the Ohm's law. one of the most important equation in this chapter. There are some questions that you will do later on where you might have to use Ohm's law like 7 times before you get the final answer. So when in doubt, Ohm's law. That's actually something that we say in physics when we're learning about circuitry. When you're in doubt, think about it. Can you use Ohm's law? Have you used Ohm's law today? Right? So when you wake up in the morning, have you used Ohm's law today? Now, okay. So let's put my pizza delivery model of circuitry into picture form. Look, I even downloaded all these pictures and put it in there. So in my format, the Pizza Hut is the battery. Okay, so that's a Pizza Hut. This is the power source. This is the pizza source because energy is in terms of that. And then we have to build rows. So these are the wires. So rows are wires. So if you don't have a row connecting to a house, we are not going to be able to deliver energy. So we have to be connecting the houses with a row, right? So then I have people who deliver pizza for me right there. Okay, so what are the houses? The houses are resistors. They are the load. Maybe they're light bulb, different light bulb, big light bulb, small light bulb, but they all want pizza, right? They all want pizza. So in my analogy, it's very easy. So we have these electrons, which has a backpack, which carries pizza, which are the voltage. So for example, this electron, so let's make a backpack for him. So this electron carries maybe 3 volts, 3 joules of energy, right? 3 joules of energy, or 3 volts. I'll just say put 3 volts in there. So every coulombs of electron carries 3 volts. Okay, so just for example. Now, that's what happened if this battery is a 3-volt battery. So if this power source. Now, what does that mean? That means every time the electron comes in, I give him 3 pizza. Okay? And then it's going to deliver 1 pizza to this person. And then after that, so it goes through that. And now it only has 2 pizza. And then it's going to go through another customer. And it's going to drop a pizza again. And it's now going to have 1 pizza. Okay? 1 volt, 1 pizza. And then it's going to go to the other last customer, and it's now going to have no pizza. Okay, and low row 2. Apparently, I deleted the row. There you go. Row is back. So now it's going to have nothing, no pizza. And then what happened? It's going to go to the Pizza Hut. And now, when you have like a 3-volt battery, for example, what does that mean is no matter how many customers are out there, I'm only producing 3 pizza at a time. Which actually makes sense in my analogy, because if you have ever been to any pizza joint, you know that they have a fixed amount of space that can actually make pizza, right? Because pizza actually needs baking, and baking needs an oven, and the oven has a certain size. You cannot stuff like 20,000 pizza in the oven because you have a lot of customers. They have to wait. They have to take turns, right? So for example, this pizza joint only has 3 ovens, so you can only make 3 pizza at a time. So therefore, this electron goes in and it's going to pick up 3 pizza. And it's going to deliver to those customer, and it's going to come back and do this again and again and again and again. Does that make sense? Now, we will actually come back to these pictures later on after a while and make them more complete and more detail. Okay, so but right now this is our model. So the number of delivery guy passing by any point per second is called current. So this actually has a current of, for example, 2 amp, and the amount of pizza that I'm making in the bakery, well, not a bakery, the pizza joint, is the voltage. So the amount of pizza they're carrying. So for example, if you actually count that, I think it's 5. If you count that as 5 volts. So these are 5 volts. So they each carry 5 volts. And then it's going to go and deliver pizza for me. So current is the number of people. Voltage is the number of people who deliver the pizza. Voltage is the number of people, number of pizza that they're carrying. Okay, so at this point, take a break, and part 2 of the video will be coming up later. Okay, so take a break at this point.